This is the complete solution for the midterm exam on linear algebra during fall semester 2017. The exam contains two parts. The first part contains 5 multiple choice questions, and the second part contains 4 problems on the following topics. So let's start with the problem 1. We're given a matrix, we need to find its inverse. So we know that if I multiply the A to the B and if I obtain the identity matrix, then these two matrices are the inverses. And basically I need to multiply this matrix to all of the 3 and see whether I'm getting the identity or not. So let's start with the multiplication of this matrix to the second one. I have to multiply this to the given matrix, which is 1, 0, minus 1, 1, 1, 0, 1, 0, minus 1, and 1. So I'm going to multiply these two matrices as a linear combination of the columns of the first matrix, where I'm going to multiply these 3 columns to the coefficients from the second matrix, right? So the first column here tells me that I just need to sum the first 2 columns. If I sum them, what I'm going to obtain is 1 over t plus 1 over t is 1, minus 1 over t plus 1 over t is 0, minus 1 over t plus 1 over t is 0. So the second column tells me that I have to multiply the second column to the 1 and the third column to the minus 1, and I have to add them, right? So if I multiply the last column to the minus 1 and add them, I will get 0 here, 1 here, and 0. And the last column here tells me that I have to multiply the first column here to the minus 1, which becomes minus 1 over t, 1 over t, and 1 over t. And I have to add this to the last column, and what I'm going to obtain is actually 0, 0, and 1. So actually this matrix is going to be the inverse of the given matrix. So the second problem, we need to do the multiplication of these 2 huge matrices. But I just need to find one entry of the resulting matrix, basically the entry at the position 2, 4. So in order to obtain this, we need to multiply the second row of the first matrix to the 4th column of the second matrix. So let's do this. So it is going to be a, B at the position 2 and 4 is equal to the 1 multiplied to the minus t, which is minus t multiplied to the minus 3, plus 6, minus t to the minus 2, it's plus 4, minus t to the minus 2, it's plus 4, 3 to the 0 is 0, minus 3 to the minus 3 is plus 9. So if I sum all of these numbers, what I'm going to obtain is 21. In the problem number 3, we need to find the statement which is wrong. So I need to go through the statements. So it seems for me that the B, C, and D are correct, and the first one is incorrect. So actually, if I would like to show or prove that one of the statements is wrong, I just need to give one counterexample. So let's assume that the U plus V is equal to the 0. Then AU plus BV is equal to the 0 for all the values of A and B. So let's choose the U as 1 and minus 1, and let's choose the V as minus 1 and 1, so that their sum is going to give you a 0 vector, 0 and 0. So now actually I can choose the A to be equal to the 2 and B to be equal to the 1. Right? So that if I multiply the A to the U, it becomes 2 minus 2. If I multiply the B to the V, it will be minus 1 and 1. And the sum of these 2 combination of the vectors is going to be equal to the 1 and minus 1, which is not actually equal to the 0 vector, right? So in this case, this statement is going to be false. Problem number 4 is about finding the row echelon form or reduced row echelon form of the matrices. So let's say we're given the matrix B in a block matrix form, and we need to find its reduced row echelon form if we know the reduced row echelon forms of the block matrices. So in this problem, we just need to look to this A as the constant. So if A would be not a matrix, but just a constant. In this case, in order to bring this matrix to the reduced row echelon form, I would just multiply the first row to the minus 1, and add this to the second. Then I would obtain A, 0, 0, right? So this is going to be this B option. So at the same time, we can just get an example. So let's assume that the reduced row echelon form of this A is equal to the 1, 0, 0, 1. right? Then the B matrix can be written, for example, 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1. So in order to bring this matrix as a reduced Rotational form, we have to multiply. So the first row to the -1, and I have to add this to the third row. There's going to be -1 multiplied to the first row plus the row 3. And what we're going to obtain is 1 0 1 0 0 1 0 1 0 0 0 0 0 1 0 1. So now we need to go to the second row and choose the pivot and eliminate all the entries below this. So if we multiply the second row to the -1 and add this to the fourth one, what we're going to obtain is 1 0 1 0 0 1 0 1 0 0 0 0 0 0 0 0. So we obtain a block matrix where I've got the reduced Rotational form here, the reduced Rotational form here, 0 matrix, and 0 matrix here. So the right option here is the B option. And the problem number 5, we need to look to the complete solution of the system of linear equations and actually guess what is the system of linear equations. Actually, so the complete solution of the system of linear equations can be written as the particular solution plus the spin of the spatial solution. So basically T1 multiplied as the first spatial solution and T2 multiplied as the second spatial solution. So if you remember, so in order to find the two spatial solutions, we need to choose the values for the free variables as the columns of the identity matrix, right? And I see the columns of the identity matrix here, so 1, 0, 0, and 1, right? So it means that the second vector, second variable, and the third variables are the free variables, right? So I need to look to the matrices A, C, or D so that the reduced Rotational form of those matrices should not have a pivot on the second column and on the third column because x2 and x3 are the free variables, right? So if I look to this matrix, I see that all the 3 columns have the pivots, right? So this is the pivot, this is the pivot, and this is the pivot. So no free variables at all. So if I look to this matrix, I see that this column has the pivot, all the elements below this are equal to the 0, and this column has a pivot. This is the pivot since all the elements below this are equal to the 0. So the only third column is the free variable, right? And only in this matrix, so the second column and the third column are the free columns. So the x2 and x3 are going to be the free variables for this matrix, and our option is going to be this one. So let's start with the first problem on the second part. So we need to find the inverse of the A using the Gauss-Jordan elimination. So in order to do this, we need to copy the matrix first of all. 1, 2, 0, 4, 2, 5, 0, 8, 3, 6, minus 1, 12, minus 2, minus 5, 3, minus 7. And just after this matrix, I have to just copy the identity matrix. And I need to bring this huge matrix as a reduced Rotational form. So I choose the pivot here, and I have to eliminate all the entries below this pivot. So basically, we're going to do the 3 operations at once. So I'm going to multiply the first row to the -1, -2, sorry, and I'm going to add this to the second row. I'm going to multiply the first row to the -3, and I'm going to add this to the third row. I'm going to multiply the first row to the 2, and I'm going to add this to the last row, so that I'm going to eliminate this 2, 3, and -2 all together. So let me do all of this operation. So please note that when we do those operations, the first row is not going to be changed. 1, 0, 0. -2, 1, 0, 0. So now if I multiply the first row to the -3 and add this to the last one, it's going to be 0, 0, -1, 0, -3, 0, 1, 0. So now if I multiply the first row to the 2 and add this to the last one, I'm going to obtain 0, -1, 3, 4 multiplied to the t plus minus 7 is going to be 1. So it's going to be 2, 0, 0, 1. So this entry on the first column, on the first row, is going to be the pivot. Now we need to go to the second row, and we're going to choose this element. And so if I want that this is going to be the pivot, I have to eliminate all the entries below this. So in order to do this, we multiply the second row to the 1, and I'm going to add this to the row 4. So what we're going to obtain is 1, 2, 0, 4, 1, 0, 0, 0. If I add all the entries on the second row to the last row, we're going to obtain 0, 0, 3, 1. So minus 2 plus 2 is going to be 0, 1, 0, 1. So now this is also the pivot, right? So I need to choose now this entry and eliminate all the entries below this. In order to do this, we multiply the third row to the 3, and I'm going to add this to the last row. So in this case, the first 3 columns, the first 3 rows of the matrix are not going to be changed. So if I multiply all the entries on the third row to the 3 and add this to the last one, I'm going to obtain 0, 0, 0, 1. So minus 3 multiplied to the 3, it's going to be minus 9. If I add this to the last one, it's going to be minus 9, 1. So 1 multiplied to the 3 plus 0 is going to be 3 and 1. So this matrix is almost in the reduced echelon form. So the only thing which I have to do is I need to multiply the third row to the minus 1. So if I multiply the third row to the minus 1, we're going to obtain 1 here, 3 here, and minus 1 here. And now I need to eliminate all the entries below above the pivot. So I need to choose this pivot, eliminate the entry above this pivot. So in order to do this, we multiply the fourth row to the minus 4, and I'm going to add this to the first. So in this case, we're going to obtain 0, 0, 0, 1, minus 9, 1, 3, 1. So if I multiply the last row to the 4, minus 4, and add this to the first one, this is going to be 0 here. 9 multiplied to the minus 4, it's 36, plus 1 is going to be 37. 1 multiplied to the minus 4 plus 0, it's minus 4, minus 12, and minus 4. The only thing which I have to do is I need to eliminate this 2, and I need to use this pivot on the second row in order to do this. We multiply the second row to the minus 2 and add this to the first one, and we are going to obtain 1, 0, 0, 0. I have to multiply all the entries on the second row to the minus 2 and add this to the first one. So minus 2 multiplied to the minus 2 is 4, plus 37 is 41. Minus 2 multiplied to the 1 is going to be minus 2 plus 4 is going to be minus 6, minus 12, minus 4. And I don't change all the other rows. So I obtained the reduced echelon form of this matrix in the form that in the left hand side I've got the identity matrix, and this matrix on the right hand side is going to be the inverse of all metrics. So now we're going to use this inverse in order to find a solution for the system when the right hand side part is going to be 0, minus 1, 1, and 0. So we can obtain the solution for the system AX is equal to the B by multiplying the inverse of the A to the B. So the inverse of the A is 41 minus 6 minus 12 minus 4 minus 2, 1, 0, 0, 3, 0, minus 1, 0, minus 9, 1, 3, 1. And we have to multiply this to the B vector, which was 0, minus 1, 1, and 0. So let me check whether the B was 0, minus 1, 1, and 0 again. So if I multiply this matrix to this vector, I need to look at this as a linear combination of the columns of the first matrix, where I have to multiply the 4 columns of this first matrix to the following coefficients. So basically, I multiply the first column to the 0, second column to the minus 1, the third column to the 1, and the last column to the 0. What I'm going to obtain is, so let me multiply the second column to the minus 1. It's going to be 6, minus 1, 0, minus 1. And I have to add this to the third column, since the third column is just multiplied to the 1. which is going to be minus 12, 0, minus 1, and 3. If I add this two column vectors, I'm going to obtain minus 6, minus 1, minus 1, and 2. And this is going to be the solution for the system of AX is equal to the B. In the second problem of the second part, we need to find the null space of this matrix. So find all possible solutions for the system AX is equal to 0. So in order to find the null space of the matrix, in the first step, we need to bring this matrix to the reduced echelon form. We choose the first non-zero entry on the first row, which is going to be 1, and I'm going to eliminate all the entries below this. We can do this by multiplying the first row to the minus 3 and add this to the second row. And we're going to obtain 0, 1, 2, 2, 0, 0. So 2 multiplied to the minus 3 is minus 6 plus 8 is 2. 2 multiplied to the minus 3 is minus 6 plus 7 is 1. 0, 0, 4, and 2. So now we need to go to the next row. So we need to choose again the first non-zero entry, and we're going to eliminate all the entries below this. So we can do this by multiplying the second row to the minus 2 and add this to the third row. We are going to obtain the matrix 0, 1, 2, 2, 0, 0, 2, 1, 0, 0, 0, 0. So this matrix now is in the reduced row echelon form, or the row echelon form. So where I've got a pivot here on the first row and on the second row. So I need to go through the columns and find the free columns. So this column and this column do not have the the pivot, so that is why they are the free columns. So that is why the x1 and x4, which correspond to the first column and fourth column, are going to be the free variables. So since we have got the two free variables, we need to find the two special solutions by solving the system R. X is equal to the 0, where R is the row echelon form of the matrix A, by assigning the values for the x1 and x4 as the columns of the identity matrix. So basically, in order to find the first special solution, we set x1 to be equal to the 1, x4 to be equal to the 0, and solve this system of the equations. We obtain x1 plus tx3, x2 plus tx3 plus tx4 is equal to the 0. If I substitute, so in the second row is going to be equal to the x3 multiplied to the 2 plus x4 is equal to 0. So if I set x4 to be equal to the 0, I can obtain that x3 is equal to the 0 from the second equation. If I substitute this one to the 0 and this one to the 0, I can obtain that x2 is also 0. Okay, now I need to find the second special solution where x1 is going to be equal to the 0 and x4 is equal to the 1. So in this case, what I'm going to do is I need to solve again the system. x2 plus 2x3 plus 2x4 is equal to the 0. 2x3 plus x4 is equal to the 0. So if I set x4 to be equal to the 1, we can obtain that x3 should be equal to the minus 1 over 2. Right? So if I substitute here minus 1 over 2, it's going to be minus 1. If I substitute the 1 here, we can obtain that x2 should be equal to, so it's going to be minus 1 plus 2, it's plus 1, minus 1 actually. So if I substitute x2 to be equal to the minus 1, I will get 0. So the second special solution is equal to 0, minus 1, minus 1 over 2, and 1. So the first special solution basically contains all the zeros, so that is why the null space of this matrix A, it's going to be just the span of the second special solution. So which is multiplied to some constant t for all values of this constant t. In the second part of the problem, we need to describe the column space of this matrix, right? So the column space of the matrix is the all possible linear combinations of the independent columns. So we've got the row echelon form of this matrix, and I see that the first, second, and the third columns are pivot columns. So that is why the second and the third column of your matrix are going to be the independent columns. So that is why the column space of the matrix is going to be the span of these two columns, 1, 3, 0, 2, 8, and 4. So we describe the null space and the column space as the span of the vectors. The third problem of the second part is about finding the row echelon form of the matrix again. So let's say in the first part we need to find the reduced row echelon form of the matrix. So we can write as 1, 0, 3, 4, 0, 2, 6, 4, 2, 0, 7, 10. So again, in order to bring this to the reduced row echelon form, which is the pivot, eliminate all the entries below this. So the first row multiplied to the minus 2 plus row 3. We are going to obtain 1, 0, 3, 4, 0, 2, 6, 4, 0, 0. So 3 multiplied to the minus 2 is minus 6, 1. 3 multiplied to the 2 multiplied to the minus 4 is going to be minus 8 plus 10. It's going to be minus, plus 2. So now we need to choose the second row. This is going to be the pivot. We eliminate all the entries below this, right? So this is already 0. And I go to the third row. This is going to be my pivot. So this is going to be the row echelon form of the matrix A. And in the second part, I need to assume that this matrix is the augmented matrix. So the matrix is called the augmented matrix, where I put the coefficient matrix and the right-hand side vector B on the same matrix. And the solution for the system AX is equal to the B. It's going to be equal to the R. X is equal to the D, where R is going to be the solution or the row echelon form of the matrix A. So I need to solve the system basically. So the x1 plus 3x3 is equal to the 4. 2x2 plus 6x3 is equal to the 4. And x3 is equal to the 2. It comes from the last equation. So if I substitute x2 to be equal to the 2 to the second one, we obtain 2x2 is equal to the 12. Plus 12 is equal to the 4. So if the 12 goes there, it's going to be minus 8. So that is why x2 is equal to the minus 4. So if I substitute x2 to be equal to the 2 to the first equation, we obtain 3 multiplied to the 2, which is minus 6. If it goes to the right, we obtain that x1 is equal to the minus 2. So the solution for the system AX is equal to the B. If I assume that this matrix is the augmented matrix, is equal to the minus 2, minus 4, and 2. So the last problem is about the idempotent matrices. So in the first part, so I just need to give 2 examples of the idempotent matrices. The easy examples would be simply the identity matrix, which is 2 by 2, or simply 0 matrix. So if I multiply the identity matrix to itself, I obtain again the identity matrix. If I obtain the 0 matrix to itself, I again obtain the 0 matrix. So in the second part, the B part, we need to consider the polynomial and find the P of A. So the P of A is going to be A in the power of 4 plus 7A in the power of 3 minus 5A in the power of 2 plus 2 multiplied to the identity, because I can't just add matrix was the constant, right? So I have to multiply this to the identity, where I'm looking to the polynomial of the matrices. So A in the power of 4 is going to be simply A, plus A in the power of 3 is simply A, and A in the power of 2 is again simply A, plus 2I. So if I simplify everything, I'm going to obtain 3A plus 2I. This is going to be the polynomial of this matrix. So in the part C, we need to prove that this matrix I minus A is again the idempotent. We can do this by multiplying the I minus A to itself. So I just need to open up the brackets. It's going to be I multiplied as I, which is I. I multiplied as a minus A is minus A. Minus A multiplied as I is minus A. And minus A multiplied as a minus A, it's going to be plus a squared. So please note that since a is a idempotent, a squared is going to be a, and I can cancel one of the terms here. And what we obtain is I minus a, which is the same as this matrix. So in the last part, we need to find the inverse of the I minus 1 over ta, right? So I need to guess some matrix so that the multiplication should be equal to I. So let's assume that this matrix should be in the form of I plus some constant multiplied to the a. So I'm interested to find this constant. So I just guessed that the inverse of this matrix should be in this form. So if I open up the brackets here, what I'm going to obtain is I plus k multiplied to the a minus 1 over 2a. And if I multiply this one to this one, we're going to obtain minus 1 over 2 k multiplied to the a squared, which is simply a again. And this should be equal to the identity, right? So basically all of these terms should be equal to the 0. So let me take out the a from the brackets. If I do this, we obtain k minus 1 over 2 minus 1 over 2k is equal to the 0, right? Only in a case when these coefficients are equal to the 0. So k minus 1 over 2k is going to be 1 over 2k minus 1 over 2 is equal to the 0. From here we obtain that the k is equal to simply 1. So if I substitute k to be equal to the 1, I obtain the matrix, which is in the form of I plus a, and this is going to be the inverse of the I minus 1 over 2a, since their multiplication is equal to the identity matrix.